Imagine a high-speed data pipeline operating flawlessly until a single malformed request hits the logic layer and the entire stream freezes solid. For most Java developers, the standard HashMap is the absolute default for key value storage, but treating it as a one-size-fits-all tool introduces severe architectural risks. Most of the time, we evaluate map implementations strictly on two criteria: how fast can it retrieve a value, and how much memory does it consume? But there is a hidden variable. The exact internal optimizations that make standard library maps so fast and efficient can be weaponized. When your server deserializes incoming data, those mechanics can be triggered maliciously to crash your system. Selecting the right data structure means looking past Big O notation. You have to understand the hidden mechanics of object graphs and recursive hashing that attackers actively exploit. Every Java map allocates memory differently to store key value pairs and organize them for retrieval. The standard HashMap is optimized for one thing: raw speed. It offers O1 constant time lookup and insertion, but the trade-off is that your keys are stored in a completely arbitrary, unpredictable order. If you need to iterate through your data in the exact order you inserted it, you use a LinkedHashMap. You keep that constant time speed, but your items stay sequential. Looking at this quadrant chart comparing lookup speed to memory overhead, you can see HashMap sitting comfortably in the high-speed, low-overhead zone. But as LinkedHashMap appears, it shifts heavily to the right. It maintains a doubly linked list across every single bucket, which requires significantly more memory. Now watch as TreeMap is plotted on the same chart. It moves down the y-axis into slower speed territory. Instead of arrays and lists, TreeMap relies on a self-balancing red-black tree. This guarantees your keys are sorted mathematically or alphabetically, but it drops your performance down to O of log n and strictly rejects any null keys. Every ordering guarantee you add taxes your system's memory and CPU. Unless your application has a strict requirement for iteration order, the standard HashMap remains the most efficient choice. Even the standard HashMap has structural limits. The worst-case scenario occurs when severe hash collisions dump multiple different keys into the exact same bucket. Historically, when this happened, that blazing lookup speed degraded. The map had to perform an O of n search, walking linearly through a long linked list of colliding entries. To fix this bottleneck, Java 8 introduced an internal optimization called Treeification. This flowchart illustrates the exact trigger mechanism. Once a single vertical linked list bucket hits 8 entries, and the total map capacity is at least 64, it instantly transforms into a branching red-black tree. Converting that dense bucket into a tree restores worst-case search times to O log n, neutralizing the algorithmic degradation caused by the collisions. If entries are removed and the bucket shrinks below 6 entries, the tree structure becomes unnecessary overhead, so it collapses back into a simple linked list. Treeification protects applications from accidental bottlenecks. However, this complex recursive internal logic creates a massive vulnerability when exposed to malicious serialization payloads. When Java rebuilds a map from a binary stream, a process called deserialization, it has to organize the incoming buckets. To do that, it automatically recomputes the hash codes of the elements being loaded. The danger lies in child recursive methods. Calling hashCode on a root container forces that container to sequentially call hashCode on every nested item inside it. One basic exploit is known as turtles all the way down. An attacker simply nests a list object inside of itself, creating an infinite loop of hash calculations. When the server deserializes this, it triggers an immediate stack overflow error. The specific thread handling the request crashes, but the broader server typically recovers. Attackers adapted to this by creating the SerialDOS payload. Instead of a single infinite loop, they build an acyclic many-to-many graph of hashset objects. Because it has a limited depth, it avoids triggering a stack overflow. This technical diagram shows the exact anatomy of the attack. Reading the root object at the bottom triggers an exponentially multiplying wave of hash computations in the hierarchical call tree expanding above it. Looking at the exponential branching arrows, you can see the math scale. A graph depth of just 100 iterations forces the server to evaluate 2 to the power of 100 hash calls. That process would take longer than the lifespan of the universe to complete. This graph demonstrates the real-world impact. The response time flatlines at a sustained, elevated plateau for 500 SerialDOS requests. The attack locks the server CPU at 100% capacity indefinitely. Because this attack specifically stays under standard memory limits, no alarms are tripped. It acts as a silent, permanent degradation of service that usually requires a hard server reboot to stop. While SerialDOS targets processor time, a similar payload known as Pufferfish is designed to attack heap memory. Instead of exploiting the hashCode function, Pufferfish weaponizes the child recursive nature of the ArrayList.toString method. This node link diagram illustrates the payload structure. It is a complex, symmetrical web of objects pointing downward toward basic 0 and 1 string values. This schematic maps the execution. The single root.read object command forces the server to stringify the root object, which causes unbound exponential string concatenation as it resolves the graph. This performance chart reveals the immediate damage. Just 5 Pufferfish requests cause a massive vertical spike in JBoss response time. The string sizes quickly exceed gigabytes, triggering an out-of-memory error and massive garbage collection overhead. These are standard library features, designed simply to make data formatting convenient. Yet, through structural manipulation, they can be effortlessly used to suffocate a server's memory allocation. Maps and sets are essential tools for high-performance computing, but their deep internal complexity makes them highly dangerous to expose to untrusted external networks. This decision scorecard outlines the baseline performance rules. You should default to HashMap for raw speed, use LinkedHashMap when building LRU caches, and reserve TreeMap exclusively for queries that require sorted range searches. On the security side, the mandate is clear. You must never blindly deserialize binary Java objects that contain these data structures from an unverified source. If you must use native serialization, implement strict whitelisting. This allows your application to actively reject unexpected map and set classes before the deserialization process even begins. The stronger architectural alternative is to avoid Java binary serialization entirely. Rely on safer, non-executable data formats like JSON or protocol buffers. Optimizing a backend requires both a clear grasp of big O memory trade-offs and a proactive defense against the computational traps buried deep inside the standard library. When you control both the core performance logic and the outer data boundary, your backend system remains completely resilient.